Hello everyone and welcome to Calc Lesson number 20. Today we're going to do our first of 2 days of section 2.5, which is going to cover implicit differentiation. There is a notes page that goes along with this that your teacher has probably sent out to you. So if you'd like to print that out to follow along, please do so now. Much of our algebraic study of mathematics has dealt with functions. In pre-calculus, we talked about two different types of equations that relate x and y, explicit and implicit. Explicit equations in x and y are such that y is isolated on one side of the equation and it equals an expression that is totally in terms of x. When I look at an explicitly defined equation, I can explicitly tell if it represents a function or not. In other words, when I see y equals the square root of 25 minus x squared, I know that for every x, there is only one y, making this equation a function. When I see y equals plus or minus the square root of 25 minus x squared, I know that for every x, there are two y values, making this equation not a function. Implicit equations are very different. Typically, they do not have y isolated on one side of the equation. Often there is a power on the y terms in the equation and both y's and x's may appear throughout the equation. For example, the equation x squared plus y squared minus 2x plus 4y plus 16 equals 0 is that of a circle. Calculus can even be applied to implicitly defined equations. Okay, so on the left-hand side here, we want to think about how we would differentiate the equation y equals the square root of 25 minus x squared. Just like we've been doing the past few days, we want to start with our rewrite steps. We'd write this as y equals the quantity 25 minus x squared to the 1/2 power. And now we can clearly see that this is the chain rule problem, where we have our 1/2 power as our outside function and our 25 minus x squared as our inside function. When we go to take the derivative, we're going to take the derivative as dy dx, the derivative of y with respect to x. Using the chain rule, we're going to bring our 1/2 down, take our exponent to the 1 less power, which would be the negative 1/2, and then leave our inside the same. Then multiply by the derivative d dx of the inside function, 25 minus x squared. Now we can actually go ahead and take that derivative of the inside function, so our dy dx is equal to, I'm going to leave this first part the same, 1/2 times 25 minus x squared to the negative 1/2 power. And now when I go to take the derivative of 25, that's a constant, just goes to 0. I leave my negative out front, bring down my 2, and take my exponent down 1 less, which brings me to 1. So I can simplify this, my derivative, dy dx. Moving whatever's necessary into my denominator, I have a let's see, my 2 and my negative 2 are going to cancel out, leaving me just with a negative x in my numerator over 25 minus x squared to the 1/2 power in my denominator, which I can, of course, also write as negative x over the square root of 25 minus x squared. So that's the chain rule that we've been doing for the past few days with our explicit functions. Now we want to look at the implicit form of this equation. So here we have x squared plus y squared equals 25. Notice we're not explicitly solved for y, so this would be an implicit equation. When we go to take the derivative here, we're going to basically do what we've been doing this whole time. So we're going to take the derivative of each piece, starting with x squared. As we do this, we are going to continue to take the derivative with respect to x. So for our first term, we have x squared. Taking the derivative as normal, we would just get 2x plus, when we go to take the derivative of y squared, remember we're taking the derivative with respect to x. So we're going to take the derivative like normal, and then we're going to incorporate that chain rule. So we're going to bring our 2 down and then take our function to the 1 less power. But then we need to take the derivative of that inside part, so we need to multiply by dy dx, which remember is just the derivative of y with respect to x. And we're going to set that equal to, now we're going to take the derivative of this side of our equation, the derivative of 25, that's a constant, is just 0. From here, we are actually going to solve for dy dx. So I'm going to start by just subtracting my 2x from both sides. So I have 2y times dy dx equals negative 2x. Now I can go ahead and divide by 2y. So I can write dy dx is just equal to, my 2's are going to cancel, this is negative x over y. And I just want to notice that these two equations are actually equivalent since y is equal to, as defined here, the square root of 25 minus x squared. Okay, so let's consider the graph of the circle that we have given. The first thing we want to do is actually find the equation of the circle in implicit form, meaning we don't need it to say y equals. So let's first recall our general equation of a circle as x minus h squared plus y minus k squared equals r squared, where our center is hk and our radius is r. So if we want to use this circle, notice we have our center here at 3, negative 2, and our radius, since we have a distance from the center to the outside, as 1, 2, 3, 4, 5, so our radius is 5, which means we can write the equation of this circle as x minus 3 squared plus y minus negative gives us a plus 2 squared equals 5 squared, or 25. So here we have the equation to the circle drawn at the right. Now we want to implicitly differentiate the equation of the circle, meaning we want to find the derivative. So as we do that, we're going to start with our first term here. X minus 3 squared is, you guessed it, a chain rule. So we can go ahead and bring our 2 down, change our exponent to a 1, leave the inside the same, then multiply by the derivative of the inside, and the derivative of x is just 1, derivative of negative 3 goes to 0. Plus, same process here, we're going to take the chain rule, we're going to take our 2 to the outside, new exponent is 1, our inside stays the same, y plus 2. Now when we take the derivative of our inside, we need to write the derivative of y, and the derivative of y with respect to x, we just write as dy dx, plus the derivative of 2 is just 0. And then the derivative of 25 is just a constant, so this goes to 0. So now, just like we did before, we actually want to solve for dy dx. So I'm going to start by moving my 2x minus 3 quantity over to the right. So I'm going to write this as 2 times y plus 2 dy dx equals negative 2 times x minus 3, dividing by 2 times y plus 2 on both sides. My 2's cancel. I am left with dy dx equals, my 2's are going to cancel. So I'm going to distribute my negative through negative x plus 3 over y plus 2. So remember that the derivative gives us the slope of the tangent line at a given point. So we're still using that same idea even when we are using implicit differentiation. So using what we found on the last slide, that same circle we have shown here, we've solved for dy dx as negative x plus 3 over y plus 2. So we want to use that to complete the table below, finding the value of dy dx at each of these indicated points, and then we're actually going to draw that graphical representation, the tangent line, on the graph. So if we're starting at 0, 2, we have an x and a y. Notice our dy dx now has both an x and a y in it. So before, we would only really need our x value. Now we need our y value too. So here, dy dx at this point, whoops, what am I doing? Is equal to, let's plug in negative 0 plus 3 over 2 plus 2 gives us 3/4. So I'm going to go to the point 0, 2. That's our point of tangency. And 3/4, remember, would be a positive slope. Looks something like that. Looking at the next one at the point 3, 3, now we have our x equals 3 and our y equals 3. dy dx would give us -3 plus 3 over 3 plus 2. Gives us 0 over 5, which remember is just 0, which is our horizontal tangent. So if we go to the point 3, 3, we'll notice that we actually have our tangent line has that slope of 0 and is horizontal. For our next one, we have the point 8, -2, xy, so solving for dy dx, we get -8 plus 3 over -2 plus 2, gives us -5 over 0, which remember is undefined. We're not allowed to divide by 0. So if we go to the point 8, -2, here's our point of tangency, we have an undefined slope, which remember is going to be that vertical tangent. And our last one on here, we want to use the point 3, -7 as our xy, finding dy dx, plugging in -3 plus 3 over -7 plus 2 gives us, again, 0 over -5, which is just 0. So looking at our function, or our circle, 3, -7, again, now we're at this bottom point. We have another horizontal tangent. Okay, we are going to do just a few more to finish up this chart, but if you are getting the hang of this, please feel free to pause the video, try them on your own, and then come on back and check your answers. So looking at the point 6, 2, but that's our x and our y, we want to find dy dx. Notice I wrote our dy dx value up top, -x plus 3 over y plus 2. Plugging in, we get -6 plus 3 over 2 plus 2, gives us -3/4, so going to the point 6, 2. Now we have a slope of -3/4, which looks something, whoops, like that. At the point -2, -2, we have our x and our y. Plugging in, we get -2 is a positive 2 plus 3 over -2 plus 2, gives us 5 over 0, which we know is undefined, which gives us that vertical tangent. And to confirm, we'll just draw that on our circle here. So we're going to go to the point -2, -2, and our tangent line there is a vertical tangent. And finally, we have the point 6, -6, plugging into dy dx. We get -6 plus 3 over -6 plus 2, gives us -3 over -4, which is just a positive 3/4. At the point 6, -6, we have that slope of a positive 3/4. So just keeping in mind that even when we are finding the derivative implicitly, that derivative still represents the slope of the tangent line on a given graph. Okay, so for our first type of example, we are just going to look at differentiating with respect to x. So we have 4 different problems here. In number 1, we're looking at d dx, meaning take the derivative with respect to x, of x cubed. And this is something we have been doing for weeks now. Just a quick notice that we are taking the derivative with respect to x, and then we have x in our equation. So here we would say that our variables agree, which means this is what we have been doing for a while, and we can just go ahead and continue business as normal, taking our derivative. The derivative of x cubed, we know we bring down the 3, take our x to the 1 less power, and our answer is just 3x squared. In number 2, however, we're taking d dx, the derivative with respect to x, of y squared. So now we're taking the derivative with respect to x of something that's not x. Oops. So in this case, we're going to say our variables disagree. So when our variables disagree, just like we saw in the beginning part of this lesson, we actually need something more. We can't just do the derivative as we always had. When the variables disagree, like we have an x and a y, we need to include dy dx to represent the derivative of y with respect to x. So when we go to take this derivative, d dx of y squared, we start out like we always would, bringing our 2 down, taking our y to the first power. Because our derivative or our variables disagree though, we need to include that dy dx. So we can write our final answer just as 2y dy dx. And because our instructions just say to differentiate, we can actually leave our response like that. Now numbers 3 and 4 are going to look a little bit more closely at the properties of derivatives that we learned earlier in the year. So for the first one, we want to take d dx, the derivative with respect to x, of a sum x plus 3y. Just like always, we can take the derivative of each piece, each term, and then add them together. So we're going to start by taking the derivative of x with respect to x. Variables agree, business as usual. The derivative of x is just 1, plus the derivative of 3y with respect to x. So the derivative of 3y is just 3. And then because our variables disagree, we need to include dy dx. And we can leave it like this. Number 4, finally, we are looking at d dx, the derivative with respect to x, of x times y squared. Because we are multiplying two different things, we need to break out the product rule where we have our first function as x and our second function as y squared. So when we go to take the derivative, remember we want our first times the derivative of the second. So our first function is x times the derivative d dx with respect to x of that second function, which is y squared, plus our second function y squared times the derivative with respect to x of our first function, which is just x. So this is where that notation really comes in handy, right? We're taking the derivative with respect to x for each of those pieces. So when we fill this in, we have x times the derivative with respect to x of y squared. We know from up here is just 2y dy dx, plus then we keep our y squared, and the derivative with respect to x of x is just 1. So we can write our final answer here, combining this to make it look a little bit nicer. X times 2y we can write as 2xy dy dx plus y squared. And we can go ahead and actually just leave it like that. Okay, so for our second set of examples, our directions are a little bit different. Now we actually want to find dy dx, which means we are actually adding an extra step after the original differentiation. We are going to solve for dy dx. So we're just adding an extra step based from what we did in example 1. So we just have a couple we're going to look at. For number 5, we have y squared plus 2 equals 2x plus 3y. Clearly not an explicitly defined equation because we have y's on both sides of our equal sign. So we're going to differentiate implicitly. So I'm going to differentiate with respect to x on my left-hand side. The derivative of y squared with respect to x would just be 2y dy dx equals the derivative of 2x with respect to x would just be 2, plus the derivative of 3y would be 3 dy dx. That is the implicit differentiation that we did in example 1. From here, we actually want to isolate dy dx. So I'm going to subtract 3 dy dx from both sides. So I'm solving for dy dx just like I would any variable. So I'm left with 2y dy dx minus 3 dy dx equals, and on my right-hand side, all I have left is 2. Notice that I now have a dy dx in both terms on my left-hand side. So I'm going to go ahead and actually pull it out. So this says dy dx, and if I pull it out to the front, what's left on the inside is just 2y minus 3 equals 2. So now to get dy dx all by itself, I can actually divide by that quantity on both sides. So my final answer, what I'm left with here, is dy dx is equal to 2 over 2y minus 3. Okay, number 6, very similar to the last one. It's just a little bit longer and a little bit more involved looking. Again, very clearly not an explicit equation solved for y, since we have multiple y's throughout at different powers. So we're going to have to use implicit differentiation here, just like we've been doing this whole time. So we're going to go ahead and take the derivative with respect to x of y cubed, bringing down our 3, taking our exponent down to 1 less, but because we are differentiating with respect to x and our variables disagree, we need dy dx, plus taking the derivative of y squared, we get 2y dy dx minus 5 dy dx minus, now x squared is the same variable, variables agree, so we can just go ahead and write our derivative as 2x, no need for a dy dx, equals, and the derivative of negative 4 is just 0. Notice that we have dy dx in 1, 2, 3 terms, but not in our minus 2x. So I'm going to go ahead and move my minus 2x to the other side so that I can try to isolate my dy dx's. So I'm left with 3y squared dy dx plus 2y dy dx minus 5 dy dx equals positive 2x. Now all 3 terms on my left-hand side have that dy dx in them, so I can go ahead and pull it out to the front. Dy dx is equal to, oops, that's not right, dy dx gets pulled out, and what's left is 3y squared plus 2y minus 5, and that is equal to 2x. So for my final step to get dy dx by itself, I can actually divide by this whole quantity on both sides, of course. And what I'm left with is dy dx equals 2x in my numerator over 3y squared plus 2y minus 5. Okay, and for our final example today, we have 2xy equals 3y squared plus 2x. And again, we just want to find dy dx. So just like we did in number 5 and number 6, we are just going to use implicit differentiation for each piece until we get to a point where we can solve for dy dx. The only catch is in our first term here, we have 2xy. So we need to actually break out the product rule. And I'm going to think of this as 2x times y. So I'm actually going to attach that 2 to my x there. So when I go to take my implicit differentiation, using the product rule on my left-hand side, I need my first times the derivative of my second. So I need my first function, which is 2x, times the derivative of y with respect to x, which I can write as dy dx, plus the second, which is y, times the derivative of the first, which would be the derivative with respect to x of 2x. Now that's only my left-hand side. I'm going to write that equal to the derivative of 3y squared would be you keep your 3, you bring down your 2y to the first. Variables disagree, so we're going to write this as dy dx plus derivative of 2x with respect to x is just 2. Now I didn't quite take this derivative yet, so I still have this piece to complete as we move down. So my next line, I'm going to still have this 2x dy dx plus y times the derivative of 2x with respect to x is just 2, so I can write this as 2y equals Multiplying my 3 and my 2, I get 6y dy dx plus 2. Now we'll notice that I have a dy dx on my left-hand side and a dy dx on my right-hand side, so I need to move both to one side and then all of my non-dy dx terms to the other side. So I'm actually going to subtract a 6y dy dx from both sides. And then I'm going to subtract a 2y from both sides, so that what I have left is 2x dy dx minus 6y dy dx equals 2 minus 2y. Hopefully you're seeing the pattern here that now that I have my dy dx's on the same side, I can go ahead, I'm going to bring this up here, and factor that out. So I have dy dx. What's left is that 2x minus 6y is equal to my right-hand side, 2 minus 2y. Then I can divide both sides by 2x minus 6y. So I can write dy dx as 2 minus 2y over 2x minus 6y. And I can factor a 2 actually out of my numerator and my denominator. So I can write my final dy dx as 1 minus y over x minus 3y. Great job with implicit differentiation day 1. For our homework assignment, homework number 20, it's on page 145, numbers 1 through 5 all, and then also number 21 and 22. If you have any questions, you can go ahead and just reach out to your teacher.